Hi, hello ib3 higher level students in our next recording. Today I'm going to present the first law of thermodynamics in a little bit different way, and then I will start to talk with you about second law of thermodynamics and about entropy, so something new to you. And our standard level lesson will be continuing viscosity and behavior of fluids, the dynamics of fluids. Now something different, but still it's a part of option engineering physics. Okay, so as you remember, I hope that first law of thermodynamics is something like law of conservation of energy for thermal phenomena. We can write first law of thermodynamics in simple way. So left part is something which happens with the system. Q means this is amount of thermal energy which is given to the system. Okay, so thermal energy given to the system. Okay, and right hand of this equation is response of the system. Delta U is internal energy of the system, change in internal energy, and W is of course work done by the system. So left hand is something which is delivered to the system. Right hand is response of the system. System as a result of, let's say, increasing of adding the thermal energy to the system can respond in two ways, or it can change its internal energy, like temperature if it's possible, or it can do a work. So work done by the system means system expands, changes volume. Okay, so this is something like a law of conservation of energy for thermal phenomena. Okay, and all of these three symbols can be or positive or negative. So Q, thermal energy of the which is given to the system. If it's positive, it means that thermal energy is going to the system. Okay, thermal energy going to the system. Okay, if it's negative, then what happens? Of course, then thermal energy is going out of the system. Thermal energy is going out of the system. Okay, the same with delta U. Delta U is the change in internal energy of the system. Of course, if delta U is positive, then internal energy of the system increases. So internal energy of the system is increasing. Okay, so if we have a gas, then temperature of the gas increases. So if we have ideal gas, which cannot change the state, then temperature of ideal gas increases. But if delta U is negative, then internal energy of the system is decreasing. So internal energy is decreasing. Okay, in the case of process without change of phase, like ideal gas temperature is going down. Okay, so system the temperature of the gas is decreasing. Okay, and the same W. Okay, what does it mean? What is a W? If W is positive, then system is doing a work. Okay, so system in the case of gas, then gas expands. Okay, when system is doing a work and our system is an ideal gas, then it expands. If W is negative, then what happens? Of course, the surroundings are doing work on the system. Okay, so surroundings are doing work on the system. So in the case of ideal gas, then gas contracts. gas reduces volume. So again, first law of thermodynamics is something like the law of conservation of the energy for thermal phenomena. Okay, so now let's focus, please copy this, and let's focus on first law of thermodynamics in the case of ideal gas and processes of ideal gas. Okay, remember, very useful in the ideal gas is Clapeyron's equation, which says that pressure multiplied by volume is equal number of moles gas constant times temperature, or we can write this for a constant amount of gas, we can write this in the form PV over T is constant. So if something happens with or pressure or volume or temperature, then other parameters, pressure, volume, of temperature, so changes, other parameters change, keeping this part PV over T at constant. Okay? So I'm going to present 4 changes. First, for constant volume, second for constant pressure, third for constant temperature, and fourth adiabatic, something new to you. Okay, so first change of the gas is known isochoric. Isochoric, or in other words, isovolumetric, means that volume of the gas is constant. Okay? So if volume of the gas is constant, then of course P over T must be also constant. So let's imagine that we have a process which is represented on the graph how pressure depends on the volume. This is the most popular graph in the thermal physics. Okay, so let's imagine that you have a gas in state, let's name the state A, and something happens with this gas. Of course, we can change temperature or pressure, so let's imagine that temperature is reduced, so at constant volume, pressure must be also reduced, so gas travels on this diagram, from A to point, let's say B, along this straight line, because isochoric means volume is constant. Okay, so let's look. In this particular case, when gas changes pressure from higher to lower, what is Q? Of course, if volume is constant, so P over T must be also constant. Okay, so if P goes down, it means that temperature also goes down. If temperature goes down, then of course our Q in our equation, Q equals delta U plus W, if temperature goes down, then Q is negative. Is it clear? Q is negative. Second, volume is constant. If volume is constant, so work is not done on the gas and work is not done by the gas. So W is equal to 0. So if Q is negative and W is equal to 0, then look on this equation, delta U, the change of the internal energy of the gas, must be negative. So what does it mean? It means that the gas is cooled down. Okay, temperature goes down, so change of internal energy of the gas also goes down. Okay? So this is first change of the gas. Isochoric. I'm going to copy this. It will be useful for next slide. Then second change is isobaric. Okay, what does isobaric mean? Baric, pressure. So isobaric means with constant pressure. Isobaric. So isobaric means that pressure is constant. So if pressure is constant, then the ratio V over T must be also constant. So let's plot the same graph, how pressure of the gas depends on the volume. Okay, vertical axis pressure, horizontal axis volume. And let's imagine that we have gas at state A here. Okay, and let's imagine that in this particular example, gas is heated up. Okay, So what happens if gas is heated up? It increases volume. So gas travels at constant pressure along straight horizontal line on this graph and arrow directed from A to B. So what does it mean? Pressure is constant. If pressure is constant, then then of course V over T must be constant. Okay, let's look on our equation. In this case, gas does a work. What does it mean? Gas expands. Volume of the gas increases, so gas does a work. So W is positive. Okay, W is positive. So what happens with, let's look here, what happens with volume? If volume goes up, then temperature also goes up. So volume increases, then of course temperature increases. So when temperature increases, then delta U, change of internal energy of the gas, is also positive. Okay? Of course, what happens with Q? If delta U is positive and W is positive, then Q is also positive, which means that thermal energy is given to the gas. Okay, is given to the system. This is the interpretation of this graph. So isobaric means constant pressure. So in this particular example, when gas expands, then W is positive, delta U is positive, and Q is also positive. Okay, so next change, it was isochoric, isobaric, so next one must be isothermal. Isothermal means at constant temperature. Okay, so when temperature is constant. Temperature is constant, look on this equation, then PV is constant, or we can write this in a little bit different form, that P is proportional to 1 over V. Okay? PV is constant, so P is proportional to 1 over V. And let's analyze the same graph, how pressure of the gas depends on the volume. So pressure on vertical axis, volume on horizontal axis. And let's imagine that we have a gas at state A here at given pressure and given volume. So what happens if gas expands? If P is inversely proportional to V, then point B of higher volume should be at lower pressure. And line connecting these 2 points is hyperbola 1 over x. Okay? So this is known as isothermal expansion. Gas expands. Okay? So let's look. Temperature is constant, which means that PV is constant. Okay? In our example, volume of the gas increases. If volume of the gas increases, then pressure must be reduced. If volume of the gas increases, it means that the gas does a work. So W is positive. In this example, gas expands, so W is positive. Okay, let's look. What is delta U? Delta U must be equal to 0. Why? Because temperature of the gas is constant. Okay, so if temperature of the gas doesn't change, then there is no change of internal energy if it's still a gas phase. We are talking about ideal gas, so it is a gas all the time. Okay, so W is positive, delta U is 0, so what happens with Q? If W is positive and delta U is 0, then Q must be, of course, positive. Okay, Q is positive due to this equation, due to first law of thermodynamics. Okay, and the last process is something new to you. Process is called adiabatic. Okay, so what does adiabatic process mean? Adiabatic. Okay, adiabatic process is a process where there is no thermal energy transfer between the gas and the surroundings. So no thermal energy transfer between the gas and the surroundings. Okay, what does it mean? It means that if gas doesn't work, then it must result in decrease in internal energy. Okay, because what is 0 here? Q is equal to 0. Okay, in this case, Q is equal to 0. No thermal energy transfer. So when gas doesn't work, then there must be reduction of internal energy. So how to represent this on our graph, how P depends on V? Graph is very similar to the previous one, isothermal, but now the point B lies closer in volume to point A. So change in the pressure of the gas is much more bigger than change of the volume of the gas. Okay, so we can say that this process is rapid. Yes, so if definition of adiabatic changes that there is no thermal energy transfer between the gas and the surroundings, then we can write that Q is equal to 0. If Q is 0, then we can write that delta U plus W is equal to 0, or delta U is equal to minus W. What does it mean? It means that if gas does a work, in our case it expands, volume increases, so in our case W is positive, then what happens with delta U? Delta U is negative. So in our case, when gas expands, so if volume rises, then delta U is negative, which means that temperature decreases. Okay, so temperature goes down. This process is rapid. Yeah. You can imagine if you have a spray or something. Then when it's not a gas, but if something is released from the tank of high pressure, okay, then it must be cooled down. Why? Because if something is released, it means that volume increases. If volume increases, then gas expands. If gas expands, then it does a work. And if it does a work, then delta U must be negative. Okay, delta U negative means gas is cooled down, so temperature of the gas decreases. Okay, so there is an equation here for adiabatic change. Okay, the equation links PV, but not in the standard way. In this case, in the case of adiabatic, we have something like this: PV to the power of 5 over 3 is constant. So if you know that process is adiabatic, so if you are sure that process is rapid, it happens very fast, that there is no time to exchange thermal energy between the gas and the surroundings, and then you can use this equation: PV to the power of 5 over 3 is constant, which means that the process is very similar in the case of PV graph than isothermal, but the line goes rapidly down. In small change in volume, there is huge change in pressure. Okay, so now you are experienced a little bit more in thermal physics. So next meeting we can start to talk about second law of thermodynamics. But today it's not the end of today's lesson. Okay, second law of thermodynamics and entropy, because to understand this, you must be more advanced in thermal physics. I'm going to give you a link to perfect documentary movie with your favorite teacher, Professor Jim R. Khalili. Yes, the same guy who presented 3 hours of story of electricity. Yes, so Professor Jim R. Khalili recorded a documentary movie which is known as Order and Disorder. Okay, and it has 2 parts. First part is energy, You don't need to watch it. You are experienced in the case of energy more, but in the case of energy he's talking also about entropy. So you can watch energy if you want, but it's not obligatory. But second part is amazing. It's about information. Okay, so he tries to prove that information is a physics quantity, and he uses a lot of thermal physics, a lot of thermodynamics, second law of thermodynamics, and entropy. Okay, so this is 40 minutes long, so please watch it. The link to the movie is in your Google Classroom in the same post. Okay, so thank you for watching. Learn physics, stay at home, and see you. Bye.